Magnets for cyclic accelerators may be warm or superconducting. Recently, it has been the superconducting magnets that have come into common use in accelerator technologies. The world's first superconducting accelerator, known as the Tevatron, was launched in 1984 at the Fermi National Accelerator Laboratory in the United States. At the time, it accelerated protons to energies of 900 gigaelectron volts. The world's largest collider so far, the Large Hadron Collider in CERN, is also superconducting. The wide use of superconducting magnets and the successful operation of accelerators based on the use of these magnets was made possible thanks to the development of cryogenic technology and the advancements in the production of superconducting materials. Up to now, a multitude of superconducting magnet structures have been invented. Let's try to classify them. They can be divided in terms of the strength of the magnetic field. Up to 2 Tesla is a magnetic low field. Up to 5 Tesla is a medium field, and equal to or greater than 10 is a high magnetic field. Superconducting magnets may or may not have an iron core. A magnetic field can be formed either by the iron core or by the shape of the superconducting winding. Through the cryostat method, one may divide magnets into submersible ones, when a magnet is submerged into a liquid helium bath, and into pumped ones, when helium is pumped by the use of special channels through the magnet. Furthermore, magnets may be divided by the phase state of the coolant. Magnets are cooled with superfluid helium, supercooled helium, and two-phase helium. The nucleotron magnet has an iron core, which is at helium temperature of 4 to 5 Kelvin while in operation. The created field is up to 2 Tesla. This image demonstrates a view of the magnet. The magnet winding is plain, and it is in direct contact with the iron yoke. Some call this magnet a window frame magnet. The key features of the nucleotron magnet lie in the fact that it has a circulating cooling system method. This is the first feature. The second is that two-phase helium is used for magnet cooling, and the decrease of the heat load is performed by vapor formation. And thus, the proportion of vapor formation in the helium flux, which flows through the magnet through special channels, changes. If the nucleotron magnet were cooled with supercooled helium, its consumption rate would be higher. A fortuitous decision on how to organize the circulating system of the nucleotron magnet was proposed in the 70s at the Laboratory of High-Energy Physics of the Joint Institute for Nuclear Research. The proposal was to cool the superconducting cable with a coolant from inside, and for the coolant to circulate inside the metal tube on which the superconductor is coiled. In these conditions, the cryogenic system of the accelerator gets substantially simplified. The amount of liquid helium used in the accelerator is reduced, and the magnet becomes more accessible. Therefore, its whole structure is essentially simplified.